Alright, fellas, let's talk logistics. We're talking about the nitty-gritty of getting stuff from point A to point B efficiently. Think about Amazon, UPS, FedEx. These giants rely on insanely complex systems to deliver your packages on time. But the core problem they face, and the thing that affects their profits, is known as the Capacitated Vehicle Routing Problem, or CVRP. It's a classic optimization nightmare. You've got a bunch of delivery points, limited trucks, and strict time windows. The challenge? Figure out the best way to get everything delivered, using the fewest trucks, the least amount of fuel, and without making anyone wait too long. It's a problem that keeps logistics experts up at night, and it's where the power of AI comes in, specifically artificial intelligence in the area of optimization. This is a complex problem to solve as the number of deliveries increases and is a great example of how AI can make a real difference. Imagine a delivery company trying to figure out the most efficient routes for hundreds or thousands of packages daily. That's a problem that traditionally makes use of exhaustive methods and a brute force method which are computationally feasible for only a small, trivial number of deliveries. This is where AI-based optimization comes into the picture. Using AI-based optimization methods will not only reduce the time for problem solving, but also greatly reduce the cost of computing. Think dozens of trucks, hundreds of stops, and specific time windows for each delivery. Without smart optimization, you're talking massive inefficiencies, wasted fuel, unhappy customers, and a big hit to your bottom line. This is not just a theoretical problem. It's directly affecting billion-dollar companies every single day. Many companies make use of AI-based solutions for route optimizations, but today, we discuss one of the emerging approaches. Now, what's the solution? Enter the Discrete Wild Horse Optimizer, or DWHO. This is a new breed of optimization algorithm, and it's designed to tackle complex routing problems like the CVRP with both precision and speed. Unlike the older approaches which use exhaustive methods, it approaches the optimization problem by simulating the behavior of wild horses. It models the horses' social interactions, their mating habits, their search for resources, and their competition. We're leveraging nature's own problem-solving skills and building an algorithm based on the process. Now, the discrete part is key because the wild horse approach is initially focused on continuous variables. To apply it to the discrete problem of determining the optimal routing of discrete steps, a discretization process is also employed. This process enhances the algorithm's capability to handle complex combinatorial scenarios. You see, the natural intelligence and ability of wild horses to navigate their environment and efficiently distribute themselves throughout large areas is what inspires this algorithm. It's not just about brute force calculation. It's about replicating a social system's innate problem-solving abilities and applying them to logistics. Using genetic operators, such as swap, reverse, insertion on its outputs enable DWHO to obtain better routes for specific problems. That's one of the key characteristics that makes it more efficient than the traditional methods. Think of it like this. Wild horses don't plan their journeys with complex maps or GPS coordinates. They rely on instinct and social interaction to find waterholes, food sources, and territories. DWHO is mimicking this adaptive behavior, dynamically adjusting its search strategy based on the specific constraints of the problem. But talk is cheap, right? Let's see how DWHO stacks up against the competition. We're going to test our strategy using the A-set and P-set benchmark datasets. Think of these benchmark sets like standardized tests for optimization algorithms. These tests are used to examine how well the algorithm performs in terms of identifying the optimal solution across a variety of problems and its convergence speed. The outcomes enable researchers to compare the performances of distinct algorithms objectively. The results will demonstrate the efficacy and efficiency of our chosen algorithm. We'll be comparing DWHO against several other state-of-the-art algorithms, including some that were tested and presented in recent publications. It's not just about throwing the algorithm at the problem. It's a rigorous process of verification, validation, and comparison. The A-set benchmark instances are often employed to assess the performance of algorithms intended for use on relatively small-scale problems, providing insight into their early-stage optimization performance. The P-set problems, on the other hand, are most often used to evaluate the efficiency and effectiveness of algorithms intended for use on medium-sized and larger-scale problems, affording an understanding of their ability to handle more complex scenarios. Through this combination, we validate the capability of DWHO to handle optimization problems of different scales. In some situations, algorithms have difficulties with the scaling of the datasets and may produce unsatisfactory outcomes as they scale to larger instances. The results from these experiments will enable researchers to compare multiple algorithms effectively. The best-known solutions for these instances are well-known in the literature. A rigorous comparison approach is implemented using specific statistical criteria, especially the Wilcoxon-rank sum test, enabling a more precise assessment of the algorithm's efficacy. The findings will highlight the superior performance of DWHO against the classical optimization techniques. These benchmark datasets provide a standardized evaluation environment that enables researchers across multiple locations and systems to compare different algorithms meaningfully. In short, we run tests on numerous instances to highlight the effectiveness of DWHO over existing solutions. And we compare it using multiple metrics, including efficiency, runtime, and accuracy, how close it gets to the best-known solution. The use of standardized tests are necessary to avoid any accidental performance. The results will reveal whether DWHO is genuinely a significant breakthrough or just another algorithm. We compare our approach with several other recent state-of-the-art algorithms. The results are in, and let me tell you, they're pretty impressive. DWHO absolutely crushes the competition for small-scale instances, often finding the best-known solution, or even better. When compared with other similar algorithms, DWHO has achieved much better results. For those tougher, larger-scale problems, DWHO still holds its own. It consistently produces solutions in most of the instances that were tested with errors of less than 1%. This means that DWHO yields both high accuracy and precision. And what about speed? In many instances, it performed faster than its competitors on the small-scale and medium-scale datasets. Even on the larger-scale problems, DWHO is only slightly slower on large-scale instances, but provides much better results. This means that DWHO not only is more accurate, but also more efficient. DWHO's consistently better results across the board are not just luck. They reflect the algorithm's inherent strengths. The statistical tests, such as Wilcoxon's rank sum test, prove this beyond any reasonable doubt. The algorithm exhibits both remarkable accuracy and speed. The proposed algorithm, DWHO, has shown remarkable prowess in effectively handling the issues of the capacitated vehicle routing problem. This is due, at least in part, to the systematic integration of local and global exploration search, and this is demonstrated via the experimental analysis performed on the relevant datasets. This ensures that DWHO can identify and exploit highly productive areas in the complex solution space, optimizing the algorithmic results and accelerating the search process. This capability was not possessed by the methods against which the algorithm was tested, and it is due to the unique approach of the proposed algorithm. We observe the advantage of the proposed DWHO algorithm compared to the other tested methods with a specific focus on comparing the computational cost and performance across a range of problem instances. This is done by comparing the obtained runtime and its distance errors using multiple metrics such as standard deviation, average, mean, and maximum. The most important thing to take away here is that the algorithm produces consistently excellent results. So, what have we learned today, guys? We've uncovered a seriously powerful new tool for solving complex logistics problems, the Discrete Wild Horse Optimizer, DWHO. This AI-powered beast consistently outperforms existing algorithms for the capacitated vehicle routing problem. And the best part? It manages this while proving to be more efficient in many cases. This algorithm is a massive upgrade over existing approaches. We've discussed its unique approach, showcasing its ability to mimic the innate optimization behavior of wild horses, leveraging the inherent intelligence of this natural system for solving complex problems. The superiority of DWHO over its counterparts has been rigorously validated through extensive benchmark testing and statistical analysis. We've seen the numbers, the graphs, and the visualizations, and the evidence points overwhelmingly to DWHO's superiority. This isn't just theoretical. These are real-world improvements in logistics efficiency, potentially saving companies millions, maybe even billions, of dollars each year. And it's doing it while simultaneously bringing about the reduction of fuel consumption, creating a friendlier environmental impact. I sincerely believe we're looking at a genuine game changer. The Discrete Wild Horse Optimizer has the potential to transform how we address the efficiency of route planning and could greatly improve various aspects of logistics, spanning from warehouse management to supply chain optimization and all the other related issues. The results presented here demonstrate that DWHO provides very good improvements over existing optimization methods, both in terms of time and accuracy, and may be a game-changing algorithm for logistics.